So now I'm going to talk about section 5.4, which is about the symmetry of Green's functions. And the whole point is we want to find out, is it true that g of r1, r2 is equal to g of r2, r1? Okay, this does happen to be true, and we're going to prove it in this video. So if we take our original Green's second theorem and we instead of phi plug in g of r1 r prime, and instead of psi we plug in g of, this should be an r1, g of r2 r prime, we can get this long equation or equality above. Okay, and the important thing to note is that both of these Green's functions have the same boundary conditions, meaning if we're using Dirichlet boundary conditions, then g of r1 and then on the surface is equal to 0. And then for this one, we would say that g of r2 r prime on the surface is equal to 0. And then if you had Neumann boundary conditions, you would just have the derivatives like at the surface. I guess you wouldn't plug in specifically the surface here. You would take the derivative and then evaluate it at the surface. But essentially, no matter whether our boundary conditions are Dirichlet or Neumann, we can do the same thing. And so what we can say in this equation is that we can say that if g on the surface is 0, this goes to 0, and this goes to 0. So if we have Dirichlet boundary conditions, these both go to 0, and then what we're left with is this whole surface integral going to 0, and then you're only left with the volume integral. And then if we have Neumann boundary conditions, this will go to 0, and this will go to 0. And then again, this whole surface integral goes to 0, and you're only left with the volume integral. So essentially what we have is we have some volume integral, and since these are Green's functions, this Laplacian and this Laplacian are going to simplify to delta functions. And so what we're left with is g is some volume integral of g of r1 r prime times the delta function of r2 minus r prime, or r prime minus r2, either way, it doesn't matter, minus our other Green's function at r2 r prime times the delta function of r1 minus r prime integrated over some volume equals 0, because again, this whole surface integral term went to 0. And so if you know how to do a delta function integral, which you should, you'll see that this is just g of r1 r2 minus g of r2 r1 is equal to 0, which implies that we have g of r1 r2 is equal to g of r2 r1. And so this is what we wanted to show. We wanted to show that they're symmetric, and we did. And so the way to interpret this is that this symmetry implies that the potential at r1 due to some point charge at r2 is equal to the potential at r2 due to some point charge at r1, assuming every problem or every surface in the problem is a grounded conductor. And so that's really the importance of Green's functions. I think one of the nice things about Green's functions being symmetric is that if you solve for the Green's function for a problem, it's easy to check if it's symmetric, and then if it's not symmetric, you know that you found the Green's function incorrectly, because Green's functions have to be symmetric according to this proof that we just did. And so that'll be it for this video. Thank you.